We start with the concept of theories. So both semantical or logical implication and proof, formal proof, are based on theories. And an L theory, so given a language L, an L theory T is simply a set of L sentences. So sentences, remember, no free variables. And we have two fundamental examples. One are axiom systems. So for example, if you have a group, you take the group axioms and put them in, collect them in a set, and that set T is the set then the theory of groups. Similarly, you can do that for fields. So then T would be the set of field axioms. You can also get a theory by starting with a structure. So suppose you have an L structure M, and you collect all the sentences that are true in that structure. That also gives you a set of sentences, and that's called the complete theory of a structure, so the theory of M. Now suppose T is an L theory, and M is an L structure. We say M is a model for T, written M models T, if the structure satisfies all sentences in T, right? And we're going to use this sigma here, usually often in place of phi now, or psi, to denote sentences. Okay, so once again, a structure is a model if it satisfies all sentences of a theory. And then we can define now that what it means that T logically implies a formula phi. Well, that just means that whenever I have a model of T, right, that model also satisfies the universal closure of the formula phi. Okay, so again, whenever M satisfies all sentences in T, it also satisfies the universal closure of phi. Or if phi is already a sentence, you don't need to take the universal closure here. So then you would just write here. So if this was a sentence, you would just write M satisfies sigma. So one should note that this is independent of the underlying language, meaning that if you take L and, for instance, you expand it to a bigger language, L prime, that L prime, that formula phi would still be an L prime formula. And strictly speaking, this notion would depend, right, on the underlying language then. But as we have seen, if we take an expansion of the language or a reduct of the language, that does not influence this model or satisfaction relation here. We contrast the notion of logical implication with the notion of formal proof. So when we prove a fact about groups, we usually start with a sentence like, let G be an arbitrary group. And then we argue using only the group axioms, which we know, of course, hold in G. Now we can ask, is there a way we can make this argument completely formal? That is, starting with the group axioms and other logical axioms, can we obtain the fact that we want to prove by means of a purely syntactic derivation? So you notice the notion of logical implication was semantical because it used the satisfaction relation for structures, right? So now we want to, however, work completely on the syntactical side. So this whole notion of proof will be a purely syntactic affair. And a syntactic derivation or proof will essentially look like this. We will arrange a proof in steps, and each step either introduces an axiom, so you pull in a new axiom that we will need for our argument. Again, that can either be a group axiom, or it can be a more general logical axiom, like a tautology or something. Or, so in our proof step, we can introduce a new formula that we obtain from the ones we've previously obtained already by means of a simple logical rule. And we will restrict ourselves to really two very simple logical rules, as we'll see on the next slide. And then the desired result, so the fact that we want to prove, will be the last step in this chain. So after we have finitely many steps, we have come to our formula that we want to prove. And if each step is one of those, is in this form here, then we have obtained a formal proof of our result. So what are the axioms, let's say beside the group axioms that we're working with, that we always have access to in a formal proof? Well, those are the so-called logical axioms, and they consist of three groups. The first group contains all first-order tautologies. So any formula of the form phi, for example, or not phi, will be accessible for us in a proof. That means we can use them as a step in our proof. Notice also that this is what is called an axiom scheme, because this we have to count for every formula, right? For every L formula of phi, we have one axiom of this form. And not only this axiom, but we also have, for example, this axiom, phi implies psi implies phi, right? So for every formula, L formulas, phi and psi, this will be a logical axiom. So that immediately implies, of course, that there will be infinitely many logical axioms, right? Because there are infinitely many L formulas. And for each L formula, again, I have such an axiom here. Well, this is, at this point, might be a little bit confusing, or at least give you a little bit reason to pause. But as we'll see later, this is not a big issue as long as we can guarantee that we can effectively recognize which formulas are first-order tautologies. The next group of axioms is also a scheme, right? Because again, for each formula phi psi and each variable x, provided they satisfy this condition here, this one will be an axiom. We've already proved this as a validity, right? So now we just make it available on the syntactical side as a logical axiom. Similar this, right? So we have for any term and for any variable x and for any formula phi, this formula here is a logical axiom. And this final axiom here is just an axiom that guarantees us that the interaction between the relation between the existential quantifier and the universal quantifier works just as we intended when we defined the universal quantifier as, so for all, we just defined to be not exists not. So again, those are the first two groups of logical axioms. Again, those are automatically result in infinitely many axioms, right? But they are of a sufficiently simple form, as we'll see later, that we can they remain governable in the sense that we can efficiently recognize whether a formula, an L formula, is actually an logical axiom. The third group of logical axioms are the equality axioms. We have already encountered them back when we talked about validities. And in particular, we know that all of these formulas, again, are validities. So there are the essentially just equality properties that in the equality symbol behaves like the equality relation on sets, right? Namely, it's an equivalence relation and it's congruent for functions and for relation symbols. And again, here for every variable x, y, and z, or all tuples xi, yi of variables, you have a separate axiom again. Because again, we're working now in a completely syntactic setting. And we can now rigorously define what a proof is. All right. So in the following, T will always be in L theory and phi will be in L formula. And a proof of phi from t is a finite sequence. So finite is important here. So a finite sequence of L formulas phi 1 up to phi n, such that, first of all, the final formula in our proof sequence is the formula we're trying to prove. Right? So phi here, so phi n is equal to 5. And in between, so for every step in the proof, one of the following must hold. So either phi I is a logical axiom, so at any time we can pull in a logical axiom, or we can pull in a formula of t. So t and the logical axioms are, in this sense, the knowledge that is given to us. And then we can use these and to create new formulas. So there of course have to be somehow rules how we can create new formulas from these two kinds of formulas. Otherwise, we would not be able to prove anything new. And there are two ways to do these, and these are the so-called rules that we can use here. So one is that at some previous point, we have derived formulas phi j and phi k, such that phi k as a formula is equal to phi j implies phi I. So this rule is called the modus ponens. And to illustrate this a little bit more, here we have, so suppose we have our proof formula, phi will be the last one, and suppose at some point we've derived the formula phi j, and at some point later in our proof, we have derived the formula phi j implies phi I. Right? Then, at any point after this, we are allowed to introduce the formula or deduce the formula phi sub I. Right? And because we have previously proved phi j, and we have also previously proved that phi j implies phi I, then we can deduce phi I. So this is the so-called modus ponens. The other rule that we use is the so-called universal generalization. So this just says if at any point we have proved phi sub j, then we can also introduce the new formula phi for all x phi sub j for any variable x. So that's again a very simple syntactical rule. So these are the two rules that allow us to prove or introduce new formulas. That is not either an axiom or in a formula in our given theory. And again, if we are able to find such a deductive sequence with phi being our last formula, right, in that sequence, then this is called a proof of phi from t. The notation, if there exists such a proof, right? So if there exists a proof of phi from t, we will use this notation here. So phi is provable from t. Note that here we have the subscript of the language, and we have to be a little bit careful now because we are in a strict syntactic setting. And if we expand the language now, we theoretically have more proofs available because there's more symbols available, right? So it's not immediately clear that this is independent of the underlying language. However, we will see this a posteriori once we prove the completeness theorem. So for now, we carry this subscript here to the provability symbol with us, but later we'll see that we can actually suppress it because it's independent of the underlying language. Let's go over a simple example of a formal proof. So we want to show that even with an empty theory, so this is just, if the theory is empty, we just don't write anything here on the left side, we can prove that for all x phi implies phi t substituted for x. Right? We already showed that this is actually a validity, right? But we argued semantically that in that case. So now we want to make a completely formal argument on the syntactical side. So we start with this. This is a quantifier axiom, right? Where we use in the, if you remember this, we stated the form. So here we would substitute, or we would plug in not phi actually for phi, right? If you look at the axiom, right? Because the axiom was phi, or scheme was phi implies exists x phi. So if we plug in not phi for phi, we get exactly this formula. So this is an axiom, that's correct. Now we also introduce a logical axiom in form of a tautology. So if you look at this formula here, this is of the form not psi implies rho, implies not rho, implies psi. Right, so this is a simple instance of the contrapositive rule, and you can easily see that this is actually a tautology. So, we are introducing a first-order tautology here, and then in the next step, since we have proved this formula and we have proved the formula this implies this, we can now imply the modus ponens on 1 and 2 to obtain this formula as a consequence of this, right? And then the last step is just, this is precisely the definition of the universal quantifier. So it's not strictly speaking a step number 4 here, but it's just reminding ourselves that this is exactly how we defined the existential quantifier. Here are a few more examples, and it's definitely a good exercise to go and try to formally prove these yourself along the lines of the previous example. So try to find the correct tautology, and then other logical axioms, and then apply the rules. A little hint for the first one, because it can be kind of tricky to pick out just the right tautology that you need. So take a look at the tautology phi implies psi implies phi and psi. And it's easily verified that this is a tautology again. Now that we have defined what a formal proof is, we of course want this notion of proof to be correct, right? Because as the way we defined it is a purely syntactic affair. So we want it, if we prove something by way of a formal proof from, let's say, the group axioms, that fact should actually hold in all groups, right? And this property is usually referred to as soundness. So we want our proof system to be sound, and that's stated in the subject of the soundness theorem. So in symbols, if phi is provable from T, then it's actually logically implied by T. And think a little bit about how you would prove this now. The basic ideas involved here is, of course, that you observe that the logical axioms are validities. So they are always true in any structure. And the two rules, modus ponens and universal generalization, hold for the logical implication relation. So what that means is that, for example, we have a set of formulas phi, and phi implies psi, right? This logically implies psi. So that means that the modus ponens holds for the satisfaction relation here, or the logical implication. And then you can prove the soundness theorem using induction on the length of a proof. To conclude this lecture, let me make a remark on the choice of our proof system. this may seem a little bit arbitrary, right? Because who tells you that the axioms that we use in our proof system, right, to define this notion here are the only possible ones? And in fact, that's not true. There are other proof systems that you could use to define this notion here. The important feature of a proof system, however, is that you get the so-called completeness out of it. So, of course, you want to have a proof system that is sound. So if you want to change the nature of your proof system, let's say you want to allow more rules, you want to allow less axioms, more rules, or something like that, you would always, of course, have to ensure that your proof system is sound, in the sense that you have this implication here. And the question that we're embarking on now is, what about the other direction? What about the direction from here to here? Right? And that will be the subject of the so-called Gödel completeness theorem. And this then says that if you have a formula as a logical implication of a theory, then you can actually find a proof of this formula. So then you want to have, of course, your proof system to be powerful enough to capture that, if this is at all possible. And we will see, that's precisely the subject of the completeness system, that for our proof system and for others possibly too, this direction here, this implication does indeed hold.